Good morning, everyone, and welcome back. In our last video, we introduced the world of offshore oil platform construction, what these structures are, and why they exist. Today, we're moving into part 2, and this is where everything begins to take shape on paper before a single piece of steel is ever cut. We're talking about planning and design, the phase where engineers, geologists, and project teams come together to make the critical decisions that will define the entire platform for the next several decades. Let's get into it.
Welcome to this explainer. Today we're diving into the source material behind a truly fascinating, high-stakes battle. We're talking about an ongoing, relentless war between human engineering and the incredibly hostile, unforgiving forces of our oceans. It's a wild ride, so let's get right into it. Okay, let's dive into this. Have you ever looked at a massive offshore oil rig, or maybe a towering wind turbine, and just wondered, how on earth do these steel giants survive for decades out in the middle of the ocean, right? I mean, we expect them to stand strong year after year, bearing absolutely massive loads. We're talking multi-ton decks, insanely heavy drilling equipment, entire crew accommodations, all while taking the absolute brunt of hurricane-force winds and relentless wave impacts. But here's the catch. The environment they live in is literally trying to tear them down from the exact moment they hit the water. So the core problem here is that these structures are exposed to highly aggressive marine conditions over really extended design lives. This isn't just a quick dip in salt water, you know? We're talking 30, 40, or even 50 years of continuous, nonstop hostility. The ocean is, well, it's basically a giant, highly conductive chemical bath. The constant presence of salt, heavy moisture, wild temperature fluctuations, and super aggressive biological growth, it all creates the perfect storm for structural decay. The ocean never sleeps, it never stops attacking, and so the materials we choose, they have to be ready for a grueling marathon, definitely not a sprint. Section 1. The first line of defense, choosing materials. You see, this massive battle actually kicks off long before a single piece of steel ever touches the water. It starts right on a designer's desk. Engineers have to make some incredibly critical initial choices to tackle this aggressive environment, and it is a complex balancing act, to say the least. They can't just pick the strongest metal in the world and, call it a day. They have to carefully juggle multiple, often competing factors. Take mechanical strength, for instance. The material obviously has to bear immense weight. But then there's fracture toughness. That's the material's ability to resist cracking under sudden stress or freezing temps. A metal might be super strong, but if it's too brittle to survive a freezing rogue wave, it's useless. Then you've got to factor in weldability, fatigue performance from years of rhythmic wave pounding, temperature effects, manufacturability, and of course, the ever-present constraint of cost. These decisions aren't just based on how a material performs on day one. Engineers are looking at the massive, long-term big picture, life cycle reliability, maintainability, and the very severe, potentially catastrophic consequences of a failure out there in a remote offshore environment. So the real trick here is how engineers deploy these materials strategically to maximize safety without completely bankrupting a project. On one side of the spectrum, we have carbon steel. This is the heavy favorite. It's the principal structural material for the underwater jackets, the decks, the massive topside frames. And why? Because carbon steel gives you a really favorable, reliable balance of strength, availability, fabricability, and cost. It is literally the workhorse of the ocean. But it's not invincible. On the flip side, we've got corrosion-resistant alloys. We're talking specialized stainless steel, duplex stainless steels, nickel-based alloys. Now, these are incredibly expensive, often costing many times more than carbon steel, because of the rare elements and super complex manufacturing involved. Because of that sky-high price tag, engineers deploy them surgically, exactly where they're needed most. Usually, that's in highly vulnerable systems directly exposed to raw seawater, concentrated chlorides, extreme temperatures, or something known as sour service. Sour service is this unbelievably hostile condition where you have highly toxic, highly corrosive hydrogen sulfide gas, which can just embrittle and destroy standard steel in no time. So, by mixing and matching these materials, we get the sheer brawn of carbon steel combined with the specialized high-tech shielding of the alloys. Section 2. Defending the three zones, a vertical battlefield. Now, what's really interesting about this is if we take a vertical journey down the offshore platform, we can actually map out how the ocean's threats and the engineering strategies needed to survive them change wildly as we move from the open air down to deep beneath the waves. Up top, in the atmospheric and marine zone, the main bad guys are harsh weather exposure and constant salt spray. To fight this, engineers use sophisticated multi-layer coating systems to throw up a really tough physical barrier. But as we move down, things get intense. We hit the splash and tidal zone. This is arguably the deadliest region of the entire structure. It demands special attention and highly integrated defense systems because the corrosion here is incredibly severe and accelerated. Why is it so bad? Because the steel right here is constantly going through cyclic wetting and drying. It gets soaked with salt water, exposed to a ton of oxygen in the air, caked in concentrated salt as the sun bakes it, and then physically smashed by crashing waves. It's a relentless physical and chemical beating. Finally, moving even further down, we reach the submerged zone. Here, fully underwater, the threat shifts completely to an insidious electrochemical attack. And that is defended by something called cathodic protection. Let's demystify that jargon for a second, because cathodic protection is a seriously fascinating defense mechanism. At its core, it uses either sacrificial anode systems or impressed current systems. Sacrificial anodes are exactly what they sound like. They're chunks of highly reactive metals like zinc or aluminum directly welded to the structure. They are literally designed to sacrifice themselves. They intentionally corrode away, taking the electrochemical hit so the main structural carbon steel is spared. Pretty clever, right? But for truly massive structures or systems that need fine-tuning over decades, engineers use impressed current systems. Instead of sacrificing a chunk of metal, this system uses an actual external electrical power source. It pumps a continuous, precisely calibrated electrical current right into the water, effectively reversing the natural electrochemical corrosive process. By actively pushing electrons onto the steel, engineers are neutralizing the electrochemical attacks happening deep underwater. It is quite literally active, electrically powered warfare against rust. Section 3. Protecting internal systems, the threat within. We've talked a ton about the devastating forces of the ocean on the outside, but here's a wild twist. The ocean is not the only enemy out there. Highly corrosive, high-pressure processed fluids, think raw oil mixed with sand, water, and acidic gases, are constantly flowing inside the pipes and machinery of these platforms, too. So to protect the internal guts of the platform, engineers have to roll out a totally different, highly specialized set of defenses. This involves building in what's called a corrosion allowance. Basically, they calculate exactly how much steel will rust away over 30 years and then intentionally build the pipes that much thicker from day one, just assuming a safe amount is going to slowly corrode. They also inject specific chemical treatments straight into the fluids to neutralize acids, and they run rigorous fluid compatibility assessments before a single drop of oil ever flows. But a really vital part of this internal defense is controlling galvanic interaction. Galvanic interaction happens when you put two dissimilar metals, say carbon steel and a specialized alloy, right next to each other inside these fluid-filled process systems. If you aren't super careful, the conductive fluid turns those two connected metals into a giant short-circuiting battery. They'll actually trigger a rapid electrochemical reaction and aggressively destroy each other from the inside out. So, engineers have to carefully design the system with electrical isolation components to stop that rapid internal self-destruction dead in its tracks. Section 4. The Integrated Master Strategy. Let's move on and see how this all builds together. This brings us to a really fundamental realization about how we build for the ultimate harsh environment. Corrosion protection isn't just a single material choice you make once on a spreadsheet and then forget about. No way. It is a living, breathing, integrated system. Effective offshore corrosion management depends on this unbroken chain of coordinated decisions across the entire life cycle of a structure. It all starts at step one with the initial material specification, making sure the absolute right alloys are chosen for the right threats. Then it moves into meticulous coating design and the engineering of those active cathodic protection systems we just talked about. But here's the thing, all that brilliant design is totally useless without strict fabrication quality. You have to make sure every single weld is perfect back in the shipyard. And crucially, engineers have to actually design for inspection access. Think about it. If maintenance crews can't physically reach a critical joint or see a hidden pipe system, they can't spot the rust. And if you can't see the rust, you absolutely cannot stop it. Finally, the strategy never truly ends thanks to long-term integrity monitoring. It takes intense, vigilant coordination from day one straight through to year 30 and well beyond, just to keep these colossal structures structurally sound and environmentally safe. So what does this all mean? We engineer incredible, resilient materials. We design brilliant, multi-layered active and passive defenses. And we constantly monitor our massive steel giants with cutting-edge technology. But with the ocean never sleeping, always attacking, and relentlessly tearing at the very molecular bonds of our structures, how long can our ultimate defenses really last?
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos.
All right, welcome to this explainer. Listen, picture the absolute most hostile, unforgiving environment on Earth. You're probably thinking of what, a scorching desert, maybe the frozen tundra? Well, today, we're heading straight out into the deep water. We're looking at massive offshore engineering structures. I mean, these are just gargantuan feats of steel and concrete, and the totally high-stakes narrative of how they battle the relentless forces of nature every single day. Just the fact that they exist out there is a massive triumph of engineering. But how do they actually survive years or even decades under constant siege? Well, that's exactly what we're going to unpack today. Okay, let's dive into this. Here's our strategic battle plan for understanding offshore survival. First up, nature's relentless ocean assault. Then, diagnosing offshore platform damage. Number 3, the maintenance counterattack. And finally, the integrity master plan. Section 1. Nature's relentless ocean assault. Okay, when we talk about the ocean in this context, we completely need to change our mindset. Forget the beautiful, calm body of water you go to for vacation. Out here, the ocean is a harsh, unrelenting adversary. Every single crashing wave, every gust of wind, every massive shift in the current, it all adds up, constantly. These structures aren't just sitting there peacefully, they are actively resisting immense crushing forces 24 hours a day, 365 days a year. And this matters immensely. We're talking about preventing catastrophic environmental disasters, protecting the actual human lives working on these rigs, and securing global energy supplies. The tension is immediate, and the threats are literally nonstop. And you know the absolute worst part? The most dangerous attacks are often the ones you can't even see right away. So here are the real culprits. The invisible enemies quietly chipping away at the platform's structural and functional reliability. We've got cyclic loading and fatigue, which is basically the constant, repetitive stress of waves slamming into the structure over and over until the metal literally just gets tired. We have corrosion, which is essentially the ocean trying its very best to dissolve the platform. There's operational wear and tear from all the heavy machinery constantly running. And then we have marine growth. Now, when I was reviewing the source material for this, I was actually pretty surprised to learn how engineers view this one. I mean, marine growth sounds kind of pleasant, doesn't it? Like a lovely, vibrant coral reef forming right beneath the surface. But to a structural engineer, oh no, it's not a beautiful reef. It is just heavy, destructive baggage. It acts like a massive sail, catching the ocean current and aggressively pulling on the platform. It's a total structural nightmare. Section 2. Diagnosing offshore platform damage. With all of those forces constantly attacking the platform, we have to treat the structure almost like a patient. Detecting deterioration before it compromises safety requires a really strict regimen of periodic baseline assessments. This is our first line of defense. Think of it kind of like checking your own car for rust or checking the tire tread, but on a massive industrial scale. You can't just wait for something to catastrophically break. You need visual examinations, meticulous dimensional checks to see if any of the metal has warped or stretched, corrosion surveys to track the rust, and coating assessments to make sure the protective layers are actually still intact. These baseline checks are absolutely vital for tracking the platform's overall health over its entire service life. But here's the thing. Sometimes just looking at the surface isn't nearly enough. And that is exactly where NDE comes in. Non-destructive examination. Think of this literally like medical procedures, but for giant steel structures. If you go to the doctor complaining of internal pain, they don't just immediately cut you open to see what's wrong, right? They use an ultrasound or an X-ray to look inside without hurting you. Well, NDE allows engineers to look deep inside the steel, the welds, and the pipes to find microscopic flaws, fatigue, and tiny cracks entirely without causing any damage to the component itself. It's brilliant. Now, what's really interesting here is the sheer variety of tools in the NDE toolkit. We've got ultrasonic testing, radiography, magnetic particle inspection, and eddy current testing. And engineers don't just use these randomly. The specific technique is chosen very carefully based on the exact component being tested and the precise degradation mechanism they're anticipating. It's highly targeted, precision diagnostics. And the tech? It's only getting better. Selected facilities are now employing massive tech upgrades. We're talking about permanent structural health monitoring systems, real-time corrosion monitoring devices, and some incredibly advanced digital data acquisition tools. This means they don't even have to wait for a scheduled checkup anymore. They have continuous condition tracking for amazingly early anomaly detection. Section 3. The maintenance counterattack. Let's move to and see how this builds from high-tech diagnostics into the gritty, physical reality of offshore maintenance. The strategy escalates very logically. Step 1 is routine preventative activities. Just doing the basics to keep things running smoothly. Step 2 is condition-based intervention. This is where those fancy NDE tests actually trigger a specific action because an anomaly was detected. And step 3 is corrective repair planning. This is when something has actually deteriorated and a major fix is required to restore safety and performance. And listen, when we say fix, we're talking about serious, heavy-duty physical tactics. We've got coating repair, anode replacement to fight off corrosion chemically, and remediating local corrosion or cracking. But even beyond that, we are talking about entire piping renewals and massive mechanical overhauls. This is incredibly dangerous, heavy lifting done by crews suspended out in the middle of the ocean, physically fighting back against the extreme damage the environment has inflicted. It's intense. Section 4. The Integrity Master Plan. So you've got the ocean attacking, you've got the inspectors diagnosing, and you've got the maintenance crews fighting back. But if these groups aren't talking to each other, the whole system completely collapses. To keep that from happening, everything is coordinated through a massive overarching integrity management framework. Think of it as the brain of the operation. It integrates absolutely everything: inspection findings, the platform's operational history, risk assessments, and rigorous engineering evaluations. This broad framework is what actually guides every single decision over the entire life cycle of the asset. And this brilliantly illustrates why strategy matters so much. A standard approach, where you're basically treating every inch of the platform equally, is essentially a blind defense that wastes precious time and resources. But our risk-based approach, that is a highly targeted chess match. It prioritizes the safety-critical or degradation-sensitive areas. By doing this, operators can optimize their inspection intervals and allocate their resources incredibly effectively. They know exactly where the ocean is most likely to break through, and they reinforce those areas first. So, the crucial point is really captured in this core philosophy from our source material. Inspection, maintenance, and integrity management shouldn't be regarded as isolated activities, but as interdependent elements of long-term offshore asset assurance. You simply cannot have one without the other. They have to breathe and move together to keep the platform standing. Which leaves us with a totally fascinating final thought. We pour staggering amounts of engineering ingenuity, non-destructive testing, intense physical labor, and complex risk management strategy into these offshore platforms just so they can survive the ocean environment right here on Earth. If asset assurance requires such an incredible interdependent web of inspection and strategy just to survive the sea, what does it take to conquer our next frontier? Imagine applying this level of integrity management to structures on the Moon or Mars. It's an absolute testament to human engineering. Thanks for joining me on this explainer. I really hope this gave you a whole new appreciation for the massive structures out there holding the line against the deep blue.
Welcome to the quiz section, Fastest Finger Edition.
You know, building a skyscraper on solid ground is an absolute logistical nightmare on its best day. But imagine taking that exact same massive structure and trying to build it while it's floating in the middle of a freezing, raging ocean. Seriously, it sounds literally impossible, right? Well, welcome to this explainer. Today we're diving deep into the digital frontiers of offshore platform construction. We're going to look way past the heavy metal and the rough seas to see how cutting-edge digital tech is just completely rewriting the rulebook. We're talking digitalization, automation, and these wild advanced data models that turn the total chaos of ocean engineering into this highly coordinated, data-driven routine. So let's jump right into the future of offshore execution, where the harsh reality of the sea meets the absolute precision of the digital world.
Okay. So let's dive into this core question. How do you safely build a massive, complex facility out in an environment that, honestly, actively wants to destroy it? For decades, the answer was basically just sheer, stubborn human willpower. Historically, this meant battling the ocean with really dangerous manual labor and just absorbing massive physical risks. I mean, you were fighting zero-visibility waters, crazy unpredictable weather windows, and brutal isolation. But today, the industry is answering this entirely differently. They realize that out-muscling the ocean just doesn't cut it anymore. Instead, they're using advanced digital models and automation to fundamentally change how these ocean giants are built. It's really no longer about out-muscling the environment, it's about outsmarting it with data.
And this text comparison perfectly illustrates the massive disconnect we're dealing with: onshore engineering versus offshore execution. Think about it. On one hand, you have the onshore engineering side, a nice climate-controlled office in Houston or London. Safe, controlled, mathematically perfect. But then you have the offshore execution, out in the North Sea or the deep Gulf of Mexico. It's chaotic, it's high stakes, and completely unpredictable. So bridging that enormous geographical gap is the ultimate challenge. And they do it by using advanced 3D digital environments. The data basically acts like an invisible tether, taking that pristine office precision and enforcing it in the harsh reality of the open ocean.
Now, when we talk about multidisciplinary coordination, we're really talking about coordinating a floating city. We have four main layers here: structural systems holding it all up, process and mechanical piping, the electrical grids powering the whole shebang, and those sprawling subsea systems anchoring it down. Trying to integrate all these layers used to be an absolute nightmare for interface conflicts. Like, imagine the disaster if an electrical grid accidentally runs right into high-pressure piping. You're talking millions of dollars and weeks of delays to fix that out at sea. But now, by using these data-linked 3D platforms, teams from all these different disciplines can coordinate simultaneously with absolute pinpoint accuracy.
So, how does this actually play out in practice? It really comes down to these three steps: constructability review, fabrication sequencing, and material tracking. Before anyone even picks up a welding torch, engineers use these models almost like a digital time machine. They run comprehensive constructability reviews right inside the software. A huge part of this is clash detection. So instead of realizing two massive pipes are going to hit each other while you're dangling from a crane 100 miles offshore, the computer flags the clash months in advance, back in that warm office. Then, teams meticulously map out the fabrication sequencing and track materials. It's like solving a giant 3D puzzle on a screen, which saves an unbelievable amount of time, money, and most importantly, human risk.
And that brings us to this absolutely crucial point about reducing manual exposure to hazardous tasks. I really want to emphasize why this matters to the workers on the ground. Yes, the tech saves money, but fundamentally, this is about keeping human beings out of harm's way. Imagine hanging off scaffolding hundreds of feet above freezing water, fighting the wind just to weld a joint. That kind of crazy exposure was just accepted as part of the job for decades. But by handing the most dangerous, physically demanding jobs over to machines, we're literally rewriting that reality. We can finally let technology take on the terrifying risks that gritty offshore workers used to just absorb every single day.
Let's actually look at that tech. Here's what automation looks like in fabrication and operations. Robotic welding, automated cutting systems, drone-based inspections, remotely operated vehicles or ROVs, and massive sensor networks. This is where heavy metal meets high-tech robotics. Inside the fabrication yards, automated systems slice through thick steel with mathematical perfection, while robotic arms handle massive welds that would just exhaust a human. And once you're actually out on the water, the tech levels up again. Drones swoop in to inspect the rig in a fraction of the time. ROVs dive into the deep, and interconnected sensor networks monitor every little vibration. It's basically straight out of sci-fi.
And this leads us to rapid data collection for subsea inspections, structural surveys, and corrosion monitoring. Think about what it used to take to verify a subsea setup. You'd have to send human divers down into extreme pressures, dealing with freezing temps, zero visibility, and very limited time. It was agonizingly slow and incredibly dangerous. Today, those divers are being replaced by tireless, pressure-proof robotic scanners. These networks give us a level of speed and precision that was just completely unimaginable a few years ago. They can safely verify complex systems in places that are literally impossible for humans to reach, instantly beaming hyper-accurate data right back up to the surface.
Now, all this data feeds into what I'd call the holy grail of modern engineering, the digital twin. As defined here, it's an asset data model that perfectly connects the original design assumptions with inspection records and real-time operational info. Essentially, it takes a massive, static physical structure out in the ocean and gives it a living, breathing digital avatar on a server back on land. This is a total game changer. Every single wave that hits the physical rig, every tiny pressure change in a pipe, it's all felt and recorded by its digital replica. The physical platform and its digital twin exist in perfect sync, giving us unprecedented visibility into the health of the entire structure.
And the real so what of this living replica is predictive maintenance. It's all about strengthening long-term integrity management and performance forecasting. By constantly feeding real-world data back into the digital model, operators can accurately predict how the platform will perform years down the line. Let's say a sensor picks up a microscopic vibration change on a specific valve. The digital twin runs the math and says, hey, based on current stress loads, this valve is going to fail in exactly 3 weeks.
The team could just casually order the part and swap it out during a routine check, way before a catastrophic failure ever happens. It flips the whole script from reacting to disasters to preventing them altogether.
But okay, let's be real for a second. You can't just buy a fully functioning digital ecosystem off the shelf. The cost of digitalization is huge. It requires massive investment in data infrastructure, a huge effort in building workforce capability, and implementing incredibly secure, cyber-resilient control systems. You need a data pipeline that can handle millions of data points every single second. Plus, there's the massive human resources challenge. You have to retrain experienced, gritty offshore workers to suddenly run complex robotics and data systems, and of course, you have to build digital walls to protect it all. Turning cash and effort into these three pillars is the steep, hidden cost of this digital frontier.
Ultimately, though, the industry completely agrees this tech is the ultimate enabler for safer, more efficient, and more predictable offshore project delivery. We are finally leaving behind the days of wild, unpredictable delays and extreme manual hazards. By fully embracing this tech, we've actually answered that massive question of how to safely build in the ocean. We've replaced the sheer chaos of the sea with a highly streamlined, incredibly safe, and super efficient project delivery model. Technology has, for all intents and purposes, tamed the logistical nightmare of the offshore environment.
But that leaves us with one seriously critical question to ponder. As offshore platforms become fully digital living assets, totally reliant on remote networks and automated sensors, how do we ensure their cyber-resilient systems can withstand the threats of tomorrow? I mean, if an ocean giant is entirely controlled by interconnected servers thousands of miles away, how vulnerable are we on this new digital frontier? It's a fascinating and honestly kind of unsettling challenge. Because as we finally succeed in removing the deadly physical dangers of the ocean, we really have to ask ourselves, are we just trading them in for the invisible digital storms of tomorrow?
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos. Drop a comment below and tell us what you'd like to see next.